Welcome to Math 201, lecture for section 2.5, the second derivative. Consider the function f graphed below. Where is it increasing and where is it decreasing? And what can you say about the values of f prime on those intervals? Okay, so where is f increasing? So I'm going to highlight some places where f is increasing, meaning that if you read the graph from left to right, when would you be walking uphill? Okay, so right here, this is all increasing from left to right. Okay, and then from here to here is decreasing. So let's mark that. In another color, we'll mark this part as decreasing. Okay, and then we have increasing again from here to here. Okay, so what I want to do is label where these are increasing and decreasing. So I've got this spot right here, we'll call that A, and this spot right here we'll call B. And this graph is increasing from negative infinity to A, unioned with B to infinity. So two intervals where it's increasing. And then it's decreasing from A to B. And then I'm supposed to observe what's true about f prime on each of these intervals. So remember, f prime is the slope of the tangent line. So I'm going to draw some tangent lines in the orange regions. So just drawing a bunch of little tangent lines, a bunch of f primes, and all of these tangent lines have a slope that is positive. Same over here. If any tangent lines I draw along this curve in the orange area have positive slope. So f prime is positive. And then in the decreasing region, if I draw tangent lines, they all have a negative slope, which means that f prime, which represents the slope of the tangent line, is negative when f is decreasing. So our conclusion of this observation is that f is increasing when f prime is positive and vice versa. When f prime is positive, that means f is increasing. And f is decreasing if f prime is negative and vice versa. If f prime is negative, f is decreasing. Okay, I've given you some tables of values, some information about f and g and their derivatives, and we want to sketch a possible graph of f and of g. I'm going to do f on the next slide. Okay, so some information about f. I know that f of 0 is 1, so I can go ahead and plot that. F of 0 is 1. And I know that f prime of 0 is 0. So I have a horizontal tangent line right here, which means that f probably does something like that. Okay. And then f of 1 is 1. So sorry, f prime of 1 is 1. So f prime of 1 is going to have a slope of 1. So I can kind of connect that like that. And then f prime of 2 is 2. So at 2, I'm even steeper. So my graph is going to go something like that. Okay, so it looks like if my tangent lines are getting steeper, my graph curves upward, and we call that concave up. F is concave up. Okay, let's look at g. So g of 0, 1 again. So let's put that in here. G of 0 is 1. So it's just a point, 0, 1. And then I have information about the derivatives. Okay, so g prime of 0 is 3, so very steep. So I've got a very steep tangent line right here. Okay. And then g prime of 1 is 1, so it's less steep at 1, right? And then g prime of 2 is 0, so like a flat tangent line. And so my graph is going to have to look something like this, and it looks like f is concave down. So what we should have observed is that when f prime was increasing, meaning the slopes of the tangent lines were getting steeper, so we started flat, steeper, steeper. When f prime was increasing, f prime being the slopes of the tangent lines, then f becomes concave up because the increasing nature of those slopes is forcing the graph to bend upwards. And then for the graph of g, the slopes were decreasing. So g prime was decreasing, meaning these slopes started very steep and got less steep and approached zero. Okay, those decreasing slopes forced the graph to bend downwards, and we got a concave down graph. The second derivative. So to track the derivative function, to track the way the derivative function f prime changes, we look at the second derivative. The second derivative of f, denoted f double prime, is the derivative of f prime. That is the derivative of the derivative. Why do we care about this? So in the case where f of x gives position and f prime gives velocity, f double prime measures acceleration, which is the rate of change of the velocity. In addition, the derivative of f prime tells us how f curves when we graph it, right? Concave up or concave down. Okay, we've come to our first activity for the lesson 2.5. So I'm going to have you pause the video, work through this activity on your own, and then come back and watch the rest of this video when you're finished. Consider the graph of the function f of x below. On which intervals is f increasing and decreasing? And what is the sign of f prime on those intervals? Okay, so I am going to highlight places where f is decreasing in one color and where it is increasing in another. Okay, let's start with decreasing. So we'll work from left to right. So we've got decreasing until we hit this minimum value down here. And then I'll switch colors for increasing till we hit that maximum value. And then decreasing again until about 4, and then increasing from 4 to 5. Okay, so let's mark the region -5 to -3. That graph is decreasing. And then -3 to -1, still decreasing. And then -1 to 1, that is my pink region, so that's increasing. 1 to 4, decreasing. And 4 to 5, increasing. Now, on each of those intervals, I want to measure the slope of the tangent line, also known as f prime. So I'm going to draw some little tangent lines in. So from -5 to -3, drawing tangent lines, these all appear to have negative slopes. And then from -3 to -1, also negative slopes. And then from 1 to 3, draw in a few little tangent lines, and we can see that those tangent lines are all have positive slopes. And then from 1 to 4, if I draw in a few tangent lines and analyze the slope, they are all negative. And then from 4 to 5, draw a tangent line or two, and you see they have positive slope. So we have affirmed this connection, right? When f is decreasing, f prime is negative. When f is increasing, f prime is positive. Decreasing, negative. Increasing, positive. So a function is called concave up if it's bending up like a cup, and concave down if it's bending down like a frown. Determine the intervals on which f is concave up or down, and what is the sign of f double prime. Okay, so let's just mark concavity. I'm going to do concave up in one color and concave down in another color. We'll start with concave up like a cup. So, oops. Okay, concave up like a cup, like there. And then it looks like it switches to concave down, down, and then up like a cup over here. Everything else looks like it's concave down like a frown. So this is all bending downwards. Right at that cusp is a weird spot, but just to the left and just to the right are both concave down. So we're going to consider that all concave down. Okay, so we need to mark the regions that are concave up and concave down. So the first region that's concave up is -5 to -3. And that is concave up. Okay, and then my next region, I'm going to say -3 to -1, concave down. -1 to 2, also concave down. And then 2 to 5, concave up. Okay, so now I want to look at f double prime, the second derivative, and determine if it's positive or negative. So the way I'm going to do that is to look at f primes and look at what is happening to the f primes. Are they increasing or decreasing, right? Because if, remember, we saw earlier that f prime positive meant f increasing, right? And f prime negative meant f decreasing. So I can apply this same rule we just learned, where I think of f prime as the function and f double prime as its derivative, right? So if f double prime is positive, that would mean f prime is increasing and vice versa. And if double prime is negative, that would mean f prime is decreasing and vice versa. Okay. So this is the same rule we just discovered. We're just, instead of applying it to f prime and f, we're applying it to f double prime and f prime. So it might be helpful if I add a little column here where I talk about f prime and state whether it's increasing or decreasing. So on -5 to -3, this first pink region here, okay, um, this graph is concave up, and like, let's look at what's happening to its tangent lines. So if I draw some tangent lines, they're all negative, right? But I'm not really interested in the sign, positive or negative, but are they increasing or decreasing? So this is a negative slope. These are all negative slopes, but they start out very steep and get less and less steep. So this is a large negative number, and then they are approaching 0. So going from a large magnitude negative number, like, I don't know, -10, and then they're approaching 0. So like -10, -6, -3, -1, those values are increasing. Okay. And if f prime is increasing, that means f double prime is positive. Okay, let's look from -3 to -1. If I draw some tangent lines, they start out almost horizontal, very close to 0, and then they get more and more negative. Okay, so they start out to 0 and they get more and more negative. That is decreasing in value. And when f prime is decreasing, f double prime is negative. Okay, next region, from -1 to 2. Okay, so this is a positive slope, positive, positive, and then it hits 0, and then it gets negative. So still getting smaller, right? So this is very big, a large positive number, but smaller, 0, negative number. Okay, so these values are decreasing, which means f double prime is negative. And then in my last region, this is negative less negative, 0, positive. So a large negative number, like maybe -5, then -2, then 0, and then a positive number like 1. So these numbers are all increasing in value, which means that f double prime is positive. So we can see a connection between the sign of f double prime and the concavity of f. Okay, so when f is concave up, we know f double prime is going to be positive. Concave up, positive, positive. And when f is concave down, f double prime is negative. Concave down, negative, negative. Okay. And the reason is because f prime is increasing or decreasing. But this is the association that we want to remember. The association between the sign of f double prime and the concavity of f. What do you think a local maximum is or a local minimum? For the function on the last page, what are the x coordinates of the local maxima and local minima? And what is the derivative at those points? So a local max is the highest point in its neighborhood. Okay, i.e. the peaks in a mountain range. Okay, so it doesn't have to be the very highest point on a graph, just just one peak in all the peaks of the mountain range. And a local min is the lowest point in its neighborhood, i.e. the valleys of the mountain range. So I've grabbed a picture of F from the previous problem, and we are supposed to look at, find the x coordinates of the local maxima and local minima, and what is the derivative at those points. So I am going to circle local maxima and local minima. So here's a valley, here's a peak, and here's a valley. So those are all the peaks and valleys. So we're going to call those local extrema. And we usually just give the x values where they are. So it looks like -1, 1, and 4 are locations of local extrema. And at 2 of those, the tangent line is horizontal. So if I draw a tangent line at this local max and at this local min, they're horizontal, which means the derivative is 0 because the slope of a horizontal line is 0. And then at one of them, we have this sharp corner, and that's a place where the derivative is undefined. Okay, because how do you draw a tangent line there? Do you draw it like this, or like this, or like this? There's no way to define how to draw a tangent line at a sharp corner, so we say it's undefined. So at these three extrema, the derivative f prime is 0 or undefined. If f prime of c satisfies the criteria you noted in number 3, right? That is, if you know that the derivative is 0 or undefined, does that mean you must have a local max or a local min there? If not, give an example where C is not a local max or a local min. So in this picture, I do have one place where I have a horizontal tangent line where my derivative is 0, um, but I do not have a local max or a local min. It's right here at -3. I have a horizontal tangent line right here, but it's not a extrema. It's not a local max or a local min. So horizontal tangent lines are not always local extrema. Say x equals -3. Okay, so here are some super important conclusions from the pictures that we've looked at today. Um, f is increasing implies f prime is positive, and vice versa. Okay, and f decreasing means f prime is negative. Okay, and then we can apply this same rule to f prime and f double prime. So if f prime is increasing, that means that f double prime is positive, and it means that f is concave up. And when f is concave down, that means that f prime is decreasing, which in turn means f double prime is negative. Okay, same information organized another way. So I've got a table with f prime, and f double prime, and what we can say about increasing, decreasing, positive, negative, concave up, concave down. Okay, so when I filled out part of it. When f is increasing, that we know that means f prime is positive. And we know nothing about f double prime, just on the fact that f is increasing, because f could look increasing like this, concave up, or like that, concave down. Those are both increasing functions f um, with different concavity. Okay, so just because f is increasing tells us nothing about concavity of or about f double prime. Okay, now if f is decreasing, that means f prime is negative and tells us nothing about f double prime, right? Because a function that's decreasing could be decreasing concave up. It could also be decreasing concave down. Okay, now if we know f is concave up, that tells me that f prime is increasing and that f double prime is positive. And if f is concave down, f prime is decreasing and f double prime is negative. Given the graph of f below, sketch the graphs of f prime and f double prime on the same axes. Okay, so this is the graph of f. Remember, to sketch a derivative, we are graphing points that have the format x, comma, slope. Okay, so it's going to have the same x values. F prime will have the same x values as f, but the y values of f prime are actually the slopes of f of f. Okay. So the easiest place to start when you're sketching a derivative are places where the derivative is zero. So I'm going to identify places where my tangent lines are horizontal. Okay, and those are going to be zeros of the derivative, right? At those x values, the derivative is zero, so I plot those x values, comma, zero. And then I find it easiest to look to the left, between, and to the right of any of those horizontal tangent lines. And I just draw one little tangent line and I say, okay, all of these tangent lines all along here are positive. Okay. And they're positive, and they are very, very steep down here, and they are getting less and less steep coming towards zero. So positive but coming down towards zero might look like, okay. All right, and then between here and here, I'm going to draw a couple little tangent lines. Okay. 1, 2, 3, maybe just a few, right? Those tangent lines are all negative. So we've got very close to zero and then more and more negative. Seems like it hits like maximum steepness right around here. And then they get less steep and come back to zero. So I have sort of a minimum negativeness. I don't know, it's hard to tell, somewhere right around here. So this is going to go down and come back. So all these y values are negative and hits maximum negativeness somewhere right around here. Okay, and then after this horizontal tangent line, my slopes then get steeper and steeper and steeper. Okay, so they just get more and more positive. So my graph is going to look something like that. So there's my f prime. Okay, and then to graph f double prime, I'm just going to repeat this process where I look at f prime as my f and look at the slopes. So I have a horizontal tangent line about right here. So I'm going to make that a 0 on my graph. Before that horizontal tangent line, my slopes are all negative. And after, the slopes are all positive and just increasing. So it's just something like that. And some people might ask, how do I know that that pink line is a line and that it doesn't curve? I don't. It could very well look like going up like that and down like that. It's hard to know. Um, okay, we've reached the second activity for lesson 2.5. I'm going to ask you to go ahead and pause your video, think about this activity on your own, and then come back and watch to check your answers. Okay, now that you have worked through this on your own, let's go through it together. Each figure below shows the graph of a function, its first derivative and its second derivative. Identify which graph is which. So I'm going to start by looking for horizontal tangent lines. I think that is the easiest way to identify potential derivatives, because wherever I have a horizontal tangent line, its derivative should have a 0 or an x-intercept. Okay, so it looks like I have a horizontal tangent line right here and right here, and maybe another one right here-ish. Now, this one has an x-intercept um, right below it, and this one has an x-intercept right above it. So it looks like the gray could be the derivative of the black, and the dashed could be the derivative of the gray. But then this horizontal tangent line has no x-intercept right beneath it. So this dashed line does not have a derivative in this picture, because if the derivative of this dashed line was graphed, it would have an x-intercept right here, which means that this must be f double prime. And because its derivative is not graphed. If its derivative were here, it would have an x-intercept where this horizontal tangent line is, but it doesn't. Okay. So f double prime is the dashed line. Okay. And then the function whose derivative is f double prime would have to be this gray curve here, because it has a horizontal tangent line right here where f double prime has an x-intercept or a 0. Okay, so the gray would have to be f prime, leaving the black curve to be f. And that makes sense because where f has a horizontal tangent line, this gray curve has an x-intercept or a 0. So the black line is f. Okay, this one is even more complicated than the previous, because all of the horizontal tangent lines have zeros, above or beneath them in the same location, the same x location. Um, so if I just mark some horizontal tangent line, I have a 0 at the same place. Horizontal tangent line, another graph has a 0 there. And then horizontal tangent line for the dashed curve, there is a 0 there. So if I can't use this to identify f double prime, I can't say there is no graph where a horizontal tangent line does not correspond to another graph that has a 0. So I have to get a little more creative, and I'm going to actually, instead of just thinking about the zeros, I'm going to think about the sign of the derivative, whether it's positive or negative. Okay, let's start with the solid black curve. Okay, so if I mark the horizontal tangent lines, then I have zeros underneath on the dashed curve. Okay, so it's possible that the dashed curve is the derivative of the black curve. Okay, so possible that the dashed curve is the derivative of solid black. Okay, based on horizontal tangent lines and zeros. Okay. Let's check that theory by looking at the sign of the slope of the tangent line. in between the horizontals. Okay, so if I draw some tangent lines, okay, between this horizontal and this horizontal, I should have put a 0 there. These pink lines have a negative slope. Okay, this is a negative slope. But between this 0 and this 0, the y values of my potential derivative are all positive. Okay. If this dashed line were the derivative of this solid line, then between these zeros, the graph should be negative because the slopes are negative. Okay, so this is not true. Okay, so it is not the case that the dashed line is the derivative of the solid black line. So we can rule that out. Okay, and that means that the gray line could also be the derivative of the black line. Okay, because this gray curve also has zeros at all the horizontal tangent lines. So this 0 and this 0 and this 0, those are all on the gray curve as well as the dashed curve. Okay, so it could be that the gray is the derivative of the solid black. Okay, and let's see if that checks out. So I've got negative slopes between these two zeros. Between my horizontal tangent lines, I have negative slopes. So between the zeros, I should have negative y values. Okay, so I think this actually does work out that the gray could be the derivative of the solid black. Okay, so this is like a check. The gray is the derivative of the solid black. But that only tells me that the solid black could be F and the gray is F prime, or it could be that the solid black is F prime and the gray is F double prime. So let's look at the derivative of the gray. Does that appear? Okay, so the derivative of the gray curve. So I'm going to draw some horizontal tangent lines and see if the derivative of the gray appears. Um, so I have a 0 here and here and here. Okay, so that means that the solid black must be the derivative of the gray. Okay, that seems unlikely that the gray is the derivative of the solid black and the solid black is the derivative of the gray. So it seems unlikely. Let's see what happens if I look at the slopes in between, right? So if I draw some tangent lines in between these two horizontal ones, these are positive, but the solid black values, y values are negative. Okay, so that is not the case. Okay, so um, that means that is the only potential derivative. So it's the only graph that has zeros in the right place to be the derivative of the gray. But it can't be the derivative of the gray because it's negative when it should be positive. So the gray curve has no derivative in this picture. So my gray curve has to be F double prime. Okay. And then gray is the derivative of the solid black. So that means the solid black would have to be F prime, leaving the dashed curve to be F. Okay, final problem, figure 3. We want to identify F, F prime, and F double prime again. So let's start by identifying some horizontal tangent lines. So I've got a horizontal tangent line, horizontal tangent line, horizontal tangent line, maybe one more over here. I just picked a random curve to start with, and I want to see if I can try to identify its derivative in this picture. So if I go down to the x-axis underneath each of these horizontal tangent lines, it does appear that I have zeros directly underneath. So it looks like gray could be the derivative of the solid black. Okay. Let's check the signs though. So the zeros work, the horizontal tangent lines correspond to zeros, but I got to make sure the signs match up as well. So if I draw some tangent lines in between the horizontal ones, These have negative slopes, and that means that the y values on the derivative should be negative, and they are. Okay, so that matches. And then these slopes are positive, and these y values are positive, and these slopes are negative, and these y values are negative. So I think gray is the derivative of black. But then the question is this f, that black is f and the gray is f prime, or the black could be f prime and the gray is f double prime? Let's see if the gray has a derivative in this picture. So I'll use another color here. So for the gray, I have horizontal tangent lines here and here and here. And I have zeros underneath on the dashed curve. So the dashed could be the derivative of gray. Okay, let's double check the signs. So in between the pink horizontal tangent lines, I'm going to draw some tangent lines. And you'll notice they all have positive slope. And the y values between the zeros on the dash curve are all positive. Okay, and then same between this horizontal and this horizontal, my slopes are negative, and the y values on the dash curve are also negative. And then my slopes get positive, and my y values on the dash curve get positive. So the dashed is the derivative of the gray. Okay, so that means that this would have to be f, and gray would be f prime, and the dashed would be f double prime.